Hello everybody. In this video we're going to be going over section 13.4, equilibrium calculations. This video is going to be a little different than the other ones in this series. We're actually going to be going over some specific calculations that we're going to be doing around equilibrium constants and equilibrium reactions. And the reason that we're going to be doing that is because there's really just a lot of different ways that we could ask these same sorts of questions. And I think it's good for you guys to kind of be able to put them into boxes and know what sort of tools you have at your disposal to answer these. Well, the first thing that we're going to do is we're going to talk about calculating equilibrium constants. Okay, so we know that equilibrium constants come from the concentrations or the pressures of the reactants and products. So we're going to have information about what those concentrations are at equilibrium. All right. If we know the equilibrium constants directly, we just have to plug them into our K expression. We have to be able to derive the K expression from the reaction and plug in those equilibrium constants. That one's pretty trivial. But if we have less information, what you're typically going to need to do is to make an ICE table to calculate the equilibrium concentrations. And the first question you're obviously going to have is, what is an ICE table? And what it is it's a convenient way of representing the changes in concentrations that occur as a reaction proceeds towards equilibrium. So here I have a model reaction that's going to move from the reactants towards the products. What I first have information about, what was told to me, is the initial concentrations. How much of this did I start off with? How much of this did I start off with? How much of that did I start off with? And I can plug those in. Now they can be zero here. Okay, for instance, if I just had started off with this reactant here, I just had ammonia in a jar, I would have that initial ammonia concentration here, or pressure, okay, and then these two would be zero. Now, as it proceeds from the left to the right, okay, we know from our reaction stoichiometry, we've been doing this quite a bit, that for every 2 moles of ammonia that I consume, I'm going to produce 1 mole of N2 and 3 moles of H2. Okay, and that's where these changes come in. All right, this is me consuming 2 moles, negative 2x. Okay, this is me producing 1 mole of nitrogen plus x. This is me producing 3 moles of hydrogen plus 3x. Then I add these together. So at equilibrium, I'm going to have the initial concentration, what I started off with of ammonia, minus 2 moles of ammonia. Okay, I'm going to have the initial concentration N2 plus however many moles of ammonia plus 3 moles of the initial concentration of H2. Okay, all I need to know is what was this shift in moles. Okay, what is my delta moles that I have across this once it's reached equilibrium? Let's see how we can go about doing that. Okay, here's one of the simpler questions that we could be asked. Iodine molecules react reversibly with iodide ions to produce triiodide ions. Okay, I have this reaction here. I'm then given some information that I need to parse through very carefully. Okay, let's read this very carefully. If a solution with concentrations of I2 and I minus both equal to 1 times 10 to the negative 3 molar before reaction, so the initial concentrations of I2 and I minus are 1 times 10 to the negative 3 molar, gives an equilibrium concentration of I2, so now I'm being given a new concentration of I2 of 6.61 times 10 to the negative 4 molar. What is the equilibrium constant for this reaction? Okay, so I was given the initial concentration of both of these, and I was given the equilibrium concentration of I2. What we do is we start filling out our ICE table. Okay, for the initial concentrations, I know those for I2 and I minus. I'm to assume from the wording in the problem that the initial concentration of I3 is 0. Okay. From the reaction stoichiometry, I know I'm going to consume a mole of I2, I'm going to consume a mole of I minus, I'm going to produce a mole of I3 minus. okay? And then I have these expressions where I'm adding these two together. So I have that 1 times 10 to the negative 3 minus x, 1 times 10 to the negative 3 minus x, and I'm going to get x for my concentration here, okay? Now, this is the equilibrium concentration of I2 right here, okay? And I was told in the problem that that is equal to 6.61 times 10 to the negative 4 molar. So I could set up this equaling 6.61 times 10 to the negative 4 molar, and then I can solve for x and get 3.39 times 10 to the negative 4 molar for x. Okay, that means that I can then fill out the rest of the table. Okay, I plug in the value of x into all these places, and I start to get this. Okay, so I can see I started off with these two concentrations. This was consumed, this was produced, and I then know what all of the equilibrium concentrations are. Now, remember that our goal was to calculate Kc. So I need to look at that reaction, come up with the expression for Kc, plug in these equilibrium concentrations from down here, and then I can finally calculate the value of Kc. Okay, in our last example, we were given complete concentration information where we could figure out the equilibrium concentrations of each of the species and asked to calculate the equilibrium constant. A different kind of problem would give you incomplete concentration information, but it gives you the equilibrium constant and it asks you to fill in that missing concentration information. All right. So an example of that would be this guy here. So let's parse through this again real carefully here. So nitrogen oxides are air pollutants produced by the reaction of nitrogen and oxygen at high temperatures. At 2000 degrees Celsius, the value of Kc for this reaction, where we have nitrogen gas plus oxygen going to 2 nitrogen oxide, is 4.1 times 10 to the negative 4. So this is my Kc. Here's my temperature. Calculate the equilibrium concentration of NO gas in air at 1 atmosphere of pressure and 2000 degrees C. The equilibrium concentrations of N2 and O2 at this pressure and temperature are 0.036 molar and 0.0089 molar respectively. So, what is important here is to realize that I am being given some superfluous information. Okay? Kc does depend on temperature and pressure, but our temperature and pressure, these values are not going to enter into our calculations. Okay? These are our red herrings. All right? The important thing that we know is the equilibrium concentration of N2, the equilibrium concentration of oxygen, and our Kc value. Let's take a look at what the math of this is going to look like. So first I write my expression for Kc that I derived from its reaction. Okay. I know Kc, I know the concentration of N2, I know the concentration of O2. All I need to do is solve for this concentration of NO. Okay. So I take this, I multiply it over, I get this expression, I take the square root, I get this expression here, I plug in those values from the problem, and I can see that my equilibrium concentration of NO is 3.6 times 10 to the negative 4 molar. Okay, let's talk now about the most challenging type of calculation that we're going to see. All right, we've seen where we're going to calculate the equilibrium constant given some concentration data. We've seen the example where we're given a little bit of incomplete concentration data and the equilibrium constant and then asked to fill in one of the concentrations. The most likely problem you're actually going to face in the real world is one where you know all of the initial concentrations and you know the equilibrium constant, but you want to know all of the equilibrium concentrations. Okay, so if you think about it, if I'm going to be putting all this stuff into a vessel, I can make measurements and know all of their initial concentrations. Equilibrium constants are well known, okay? I can often look them up for a specific reaction, but what I want to know is when this reaction is done, what are those equilibrium concentrations going to be? Now for these problems, we're going to have a 4-step approach. All right, the first thing we're going to do is I'm going to identify the direction in which the reaction proceeds to reach equilibrium. We can't take that for granted, okay? We need to figure out, is this going to go from the left to the right or the right to the left? The second thing we're going to do is develop our ice table. The third thing we're going to do is calculate the concentration changes and subsequently the equilibrium concentrations, okay? We're going to do this from values that we have in our ice table. The last thing we're going to do is we're going to confirm that what we found was actually true. So we're going to do a little check. Let's go through our example here. So under certain conditions, the equilibrium constant Kc, so we're dealing with concentration equilibrium here, for the decomposition of phosphorus tetrachloride gas into phosphorus trichloride gas and chlorine gas is 0.0211. Okay, so Kc equals 0.0211. What are we being asked for? What are the equilibrium concentrations of all three of the species in a mixture that initially contained only phosphorus pentachloride at a concentration of 1 molar? Okay, so the first thing I need to parse out here is the phrase decomposition of phosphorus pentachloride into phosphorus trichloride and chlorine gas. All right. At this point, we should be able to recognize that that represents this reaction right here. Okay? We're being told the initial concentration of the single reactant right here with the last phrase here. It initially contained only phosphorus pentachloride at a concentration of 1 molar. Now, the next thing we can do is develop our ice table from there. Okay? We know the initial concentration of the phosphorus pentachloride. We know the other ones are not present initially. That will not be true for every case, but it is true given the language in our problem. Next, we look at the change. For that, we have to look at the reaction stoichiometry, and we see that they are all ones here, which means that all we have to do is deal with the sign. Because this is being consumed, it's got a negative. Because these are being produced, they get positives. We add them together and we get our equilibrium expressions for each of the species. After that, we go to our Kc. We write the Kc, again with the products over the reactants, okay? Our exponents were easy this time. They were all 1, okay? And we start substituting in for these values the expressions we have down here in the ice table. Okay, so this guy becomes x, this guy becomes x, this guy becomes 1 minus x. All right, if we take the product of these two, that's x squared. All right, and this whole thing is equal to the Kc that we were given in the problem. That was 0.0211. Now we need to look at just this portion and do some algebra. Okay, what we're going to do is we're going to multiply this whole denominator here over to the other side. I get x squared left on that side is equal to this guy times that denominator right there. I distribute that. I get this expression right here. Okay, I start subtracting these terms over to the other side and I get a proper quadratic equation here. Now, I'm not showing you how to use the quadratic formula here, nor do I care how you go about getting these roots, okay? You could use the quadratic equation. There's an example in the book of how to use the quadratic equation. You could put these coefficients into any number of online calculators that are able to give you the roots for a polynomial, okay? In the end, you're going to find the roots, okay? And we have to make a choice now. What we need to realize is that X is a concentration, okay? It is a number of moles, and therefore cannot be a negative value. It can't be a negative value, and it can't be in an imaginary number. Typically, you are going to get a single root that has a positive value, okay? There is an example in the quiz that I gave you where you do not know that, okay? You were actually given two reasonable roots when you solve for it, but I did give you a hint about which one to choose in that case. Now we can substitute X into our concentration expression. Okay, so all we're doing here is going back to these expressions and just putting X in here. Okay, so the phosphorus pentachloride, for instance, is 1 minus X. 1 minus X is going to be 0.87 molar. The other two are just X. They're equal to each other, and they're both 0.135 molar. Now we know our equilibrium concentrations, and we go back to our definition of Kc, and we plug them in, and we see that that does in fact equal the Kc that we know. So that's our check to make sure that these concentrations are correct. All right. Now, when we did this, we had to solve a polynomial, and that is a bit burdensome. And these questions do not have to get very complicated. The stoichiometry doesn't have to get very complicated for this to become very tricky polynomial to solve, right? We can solve regular quadratics where we have x squared here, but once we get to a cubic and x to the fourth, a fourth power polynomial, the answers get to be more difficult. And once you get to x to the fifth power, you actually have to solve that numerically. There is no analytical way to solve it, okay? Like we normally would here. You have to use some kind of numerical method with like a calculator and an algorithm and stuff to solve that. So we can avoid doing this by making a clever approximation, okay? But we have to make sure that certain conditions are met for this approximation to be valid. Now, when the change in concentration, so that's our X, is significantly less than the initial concentration, the initial concentration experiences a negligible change. Okay? This occurs, this is true, when we have a small value for K. Okay, so you should be watching for small values of K. When these conditions are met, a clever approximation can be used. Let's take a look at an example where we can apply our approximation. Okay? What are the concentrations at equilibrium of a 0.15 molar solution of hydrogen cyanide? So we can see that in this problem, rather than giving us words that we need to parse through, okay, it's relaying a lot of information just with this equation right here. Okay, so rather than giving us words we need to parse through to find our reaction or to figure out what Kc is, it's just telling us this. Okay, and students have trouble depending on the type of learner you are going from one to the other. Okay, some people like a lot of words and then they're able to write this out, and some people see just a short thing like this and it's a little confusing about what we're meaning here. But we now know Kc, okay? From the language here, we're going to assume that the initial concentration of our protons and our cyanide anions are 0, okay? We can see that Kc is 10 to the negative 10, meaning it's small, and that would key us in that we can make an approximation here, okay? So for our initial concentrations, we're going to have the value of HCN here. That is our reactant, okay? Because we only have reactants here, we know it's going to proceed left to right instinctually, but QC would equal 0, which is less than even the small Kc value. So we know left to right, okay? We have 0 and 0 here. We're consuming hydrogen cyanide. We're producing H plus and Cn minus. Okay, we add those together to get our expressions for our equilibrium concentrations. Now, normally, after we plugged in for our Kc, okay, we would have gotten a square up here and this down here, and we would have wound up with the quadratic like we saw before. But here we're going to do a clever little approximation. The approximation is that this x here is so small, it's not going to change this value. And this whole expression here is well approximated as staying at 0.150. Okay? If that's true, Kc is approximately going to equal this expression right here. Now all we have to do is multiply this over. So I have 0.15 times Kc and take the square root of x. All right. And I'm going to take the positive root of that. Okay. Remember that when you take a square root, you get a positive and negative root. Okay. But we know x is never negative, so I just take the positive root of that. Then I go back to those expressions that I had in my ICE table here, and I start plugging in x. Okay, and I can get all of my concentrations. What you're going to see is that when you go to calculate the change in concentration of the hydrogen cyanide and you apply your sig figs, okay, that concentration doesn't change. Okay, if you go to plug x back in after you made this type of approximation for that guy that's on in the denominator where you did that, okay, and it does appreciably change, you are wrong and you cannot use the approximation. Okay, you should see that this guy's concentration remains roughly the same, and then you can calculate the molar concentration of the other ones, which should be in this case small, because again what we're saying is that this reaction does move a little bit to the right, but not very much. Okay, only sparingly. There's only going to be a slight shift here. That's what makes this approximation here valid.